Got a bad noise, Joe?
Yep, I think I got a bad lifter.
That sounds like more than one.
I'm gonna put in a whole new set.
Yeah, that might fix it, but what kind of oil pressure do you have?
Well, I don't know, what's that got to do with it?
Well, first, the lifters are hydraulic, so they rely on oil pressure to stay pumped up, right?
Right.
And second, the lifters are actually quite a ways down the line from the oil pump. So if the oil pressure is low, the effect is first going to be felt furthest from the pump.
Whoa, how'd you get so smart on engine lubrication systems?
You know, I went to the Ford new model class last week.
Yep.
I got into a real discussion on lubrication systems with the instructor when the class was over. And with these new grade oils and G-rotor oil pumps and everything, I was really getting confused. Well, the instructor spent some time and really helped me out. Yeah, he set me straight on a lot of things. Say, JC, I'm a little confused over some of the things you were mentioning when you went over the lubricating system. I haven't been a technician that long. I'd really like to learn some more.
No problem, John. Do you want to talk about just the engine we discussed in class, or do you want the full treatment?
Well, the full treatment if you've got the time.
Well, sure, I've got the time if you do. It won't take that long, and I'll make an expert out of you. Well, let's start by figuring out exactly what the lubrication system is for. Now, basically, it prevents the engine from wearing out by providing a barrier of lubricating oil between moving parts. The oil prevents metal-to-metal contact, but the lubrication system does even more. Let's take a look at this video disc so you can see what I mean. The lubrication system actually has 5 functions, which are to lubricate, seal, cool, protect against corrosion, and clean the engine. Let's take a look at each of these functions. As I said, the basic purpose of the lubrication system is to prevent the engine from wearing out. And this means lubricating the engine by maintaining a slippery surface between moving parts. The oil has to be able to adhere to the metal surface and resist being shoved away when either hot or cold. The next function is to seal. As you know, immediately following the burning of the fuel in the combustion chamber of an engine, gases are formed which are under high pressure. It's the pressure of these gases on the piston head which causes the engine to run. So, it's necessary to keep these gases from leaking past the piston rings. To seal the gases in, the oil film on the cylinder walls makes up for microscopic unevenness in the fit between the rings and the walls. The film fills in any gaps through which the gases might escape. The next function is cooling. Now, I'm sure you're already aware that the great mass of unwanted heat in an engine is removed by the cooling system.
Right.
But there are parts in the engine that rely on oil to cool them. Bearings are a good example of components that are cooled by oil. What happens is that relatively cool oil is pumped in, lubricates, and then at the same time absorbs heat, then carries the excess heat back to the crankcase where it is dissipated. The next function of the lubrication system is corrosion protection. It's important to remember that there are always some combustion products that blow past the rings, and the blow-by is typically at its worst when the engine is cold and there is a rich air-fuel mixture. The blow-by contains a variety of combustion waste products. These include water, unburned fuel, soot, carbon, and acids. And many of these materials remain in the engine and contaminate the oil. That's why it's important for the oil to contain additives that coat the metal components of the engine to prevent corrosive damage. The final function of the lubrication system is to keep the engine clean. The oil does this by keeping contaminants in suspension. This is extremely important because if the contaminants remain in the engine, they can build up, causing deposits. Take a look at this severe sludge problem. What happened is that blow-by products escaping past the piston rings were absorbed by the oil and formed in the sludge. Additives within the oil should have forced these compounds to be dispersed in the oil, not to collect in the engine. With the waste materials dispersed properly in the oil, the filter can trap the larger particles, and then any of the contaminants too small to be filtered are removed right with the oil during an oil and filter change. Well, so far we've discussed the purpose and functions of the lubrication system. Let's review them one more time before we move on. The basic purpose of the lubrication system is to prevent the engine from wearing out. It accomplishes this through the 5 functions, which are to lubricate, seal, cool, protect from corrosion, and clean. There are 2 basic lubrication systems that you should be familiar with. They are the dual filter system and the full flow system. The difference in these 2 systems is basically in the filtering method. Let's take a look at the full flow system first. In this system, oil is picked up by the oil pump and is first filtered and then delivered to the bearings and other engine components. It gets the name full flow because all the oil goes to the filter. The full flow lubrication system is used on all current Ford automobile and light truck applications. The dual filter system is used on some small automotive diesel engines, but is more common in medium and heavy-duty trucks. This type of system is used to assist in controlling heavy particulate contamination. In this system, the majority of oil flows to the main full-flow filter. A small portion of the oil flows to a bypass filter, which typically is capable of capturing even smaller particles than the full-flow filter. Oil that goes through the bypass filter is returned directly to the oil pan. The dual filter system is quite efficient in that it has 2 filters, allowing more efficient removal of particle contaminants contained in the oil. Well, now that you're familiar with the dual filter and full flow systems, let's take a look at a complete lubrication system and see the oil flow. The lubrication system we'll look at for our example is one that would be common on V8 engines. Oil flow begins in the oil pan, which is the reservoir for holding the engine lubricant. At the bottom of the oil pan, there is a strainer, which is the pickup for the oil pump. As the engine is started, oil flows through the strainer into the oil pump. The oil pump pressurizes the oil and forces it through the oil filter. The oil filter is responsible for removing particles carried by the oil. Oil enters through several ports around the perimeter of the filter, is forced through the filter element, and then leaves the filter through its center opening. From the oil filter, the oil goes to the main oil gallery. The main oil gallery feeds the pressurized oil to the main and rod bearings. The main bearings are lubricated first. Then, drillings in the crankshaft route oil to the rod bearings. Also, oil from the main bearings is routed to the camshaft bearings through drillings in the block. Okay, so far we've seen how the bearings are lubricated. You should have noted that the bearings were all pressure fed. Now let's take a look at how the upper engine components are lubricated. Off the main oil gallery, there are 2 other small galleries which feed the hydraulic lifters. The lifters need this oil to maintain zero lash and also to lubricate the upper part of the engine. In this design, the upper part of the engine is lubricated by oil that travels through the hollow push rods from the lifters. It functions in this manner. Oil flows into the lifter from the oil gallery through a hole in the lifter body and plunger. There's also a hole in the push rod socket that allows pressurized oil into the push rod. While the lifter is on the base circle of the camshaft, oil is allowed to flow into the oil chamber beneath the plunger. As the camshaft turns and the lobe contacts the lifter body, the pressure on oil in the lower chamber forces the check valve closed, making the lifter a solid component in the valve train, and the lifter rises. Although there is no more oil flow into the lower chamber, there is still oil flow into the upper chamber and out to the push rod because the check valve does not close this chamber off. From the push rod, the oil sprays out over the rocker arm and other valve train components. This spray coats the upper engine components with oil to provide the necessary lubrication. Now, what I want you to note here is that lifters were pressure lubricated, but the upper engine components, meaning the rocker arms, valves, and valve springs, are lubricated by a spray. The oil then drains back from the cylinder head to the oil pan. That's how the basic lubrication system works.
But JC, you left out some parts. How are the camshaft lobes, pistons, cylinder walls, timing chain, and piston pins lubricated?
Well, that's a good point, John, and I was going to get to that. As the engine is running, A certain amount of oil is escaping from each of the bearings and is sprayed throughout the engine, or is dripping downward from the force of gravity. It's this spray and dripping which provide a lot of the lubrication for the camshaft lobes, pistons, cylinder walls, timing chain, and gears, and the piston pins. In addition to the spray that typically comes off the bearings, some engines are designed to provide a more direct spray of oil to the cylinder wall through a squirt hole in the connecting rod, which provides a spray of oil under the cylinder wall as the engine runs. The excess oil on the cylinder wall is scraped off by the oil control ring and drains through these return holes cut in the piston ring groove. The splash of oil coming through the return holes is what lubricates the piston pin. Some diesel engines used by Ford lubricate the piston pin with pressurized oil rather than by a splash. In these applications, the connecting rods are rifle drilled. This rifle drilling allows oil to be routed to the connecting rod piston pin bushing from oil passages drilled in the crankshaft that feed the rod bearings.
Well, I see how the major components of the engine are lubricated, either by direct oil pressure or by some method of spray or dripping. But I'm confused about all the different engines. There's overhead cams, dual overhead cams, rocker arm shafts. There's all kinds of differences.
Well, those are good points, but what you've got to remember is that typically there is a basic feed pattern. Now here's the basic feed pattern. Oil pan to strainer, to pump, to filter, to bearings is pretty well set and won't change much between engines. It's the upper part of the engine where you'll see differences. And really, you brought it up yourself by mentioning the different upper engine designs, like the overhead cam, dual overhead cam, and rocker arm shaft. These components, like any other, must be lubricated, and it's typically through an oil passage. Let me show you some examples. In this 4-cylinder overhead cam design, you can see there is an oil passage right off the main oil gallery. This passage feeds another gallery in the cylinder head, which in turn pressure feeds the camshaft bearings and lifters. Also note that the camshaft is hollow, and each individual camshaft lobe is pressure-fed oil. The other components, such as the valve components, are lubricated by spray and dripping oil. A point to note is that not all overhead cam engines utilize the hollow camshaft as an oil gallery. In these other applications, the camshaft lobes would be lubricated by spray or dripping oil. In a dual overhead camshaft application, the lubrication happens in a very similar manner. This example shows a V6 dual overhead camshaft engine. Here the oil is fed to each cylinder head through a passageway. Inside each cylinder head, there is an oil gallery which pressure feeds the camshaft journals and lifters. The other components, including the camshaft lobes, are lubricated by spray and dripping oil. Now, the final design you mentioned was the rocker arm shaft.
Right.
In this design, usually the rocker arm shaft is hollow and acts as the oil gallery. Here, oil is routed through a passageway off the main oil gallery to the rocker arm shaft. The rocker arm shaft then distributes the oil to the rocker arm bushings under pressure, and then to the other valve train components in the form of a spray or dripping oil.
Wow, there sure is a lot to these lubrication systems.
Yes, there is. But what you've got to remember is that there's 3 basic lubrication methods: pressure, spray, and drip. Main bearings, rod bearings, and cam bearings will always be pressure fed. Sometimes the piston pin and rocker arm bushings are too. Typically, other components are lubricated either by spray or from dripping oil. But you've got to be on the alert for differences in lubrication systems. Take the 2.3-liter engine. It has a hollow camshaft with an oil feed to each lobe. The 1.9-liter is also an overhead cam, but it does not function as an oil gallery for the camshaft lobes. They are lubricated by spray and dripping oil. Now, if you're wondering about how the lubrication system is organized, or if there are any special points to be aware of, take a look in the shop manual. Each engine section typically contains a description of the lubrication system. Now, the next thing I want to talk to you about are 2 of the major system components, the oil pump and the oil filter. There are different designs that you should be aware of, and they have the ability to change the flow of oil under certain circumstances.
Are you going to talk about the relief valve in the oil pump and the bypass valve in the oil filter?
Yes, I am. They're the components that I was referring to that can change the flow of oil. Let's start with the oil pump. We'll look first at the conventional oil pump, typically driven by a shaft off a gear on the camshaft. There are two basic design differences in the conventional oil pumps, and they have to do with the pumping elements. The first is the gear type design. In this oil pump, there are two spur gears, a drive gear and a driven gear, mounted in a close-fitting housing. When pumping, oil is carried around the outside of each gear in the space between the gear teeth and the case. As the teeth mesh in the center, oil is forced out, producing oil pressure. The rotor-type oil pump is essentially a special lobe-shaped gear meshing with the inside of a lobed rotor. The center lobed section is driven, and the outer section idles. As the pump rotates, it carries oil around between the lobes. As the lobes mesh, they force oil out under pressure in the same manner as the gear-type pump. You'll find that most of the oil pumps used in Ford engines have rotors rather than gears. The other type of oil pump that is used by Ford is driven by the crankshaft. This pump mounts directly to the front of the engine. It functions in the same manner as the conventional rotor pump that we just discussed. The inner rotor is driven, this time by the crankshaft, and the outer rotor idles. Oil is forced out as the lobes come in contact. The primary advantage of using this style of oil pump is that it's a space saver because it is integral with the engine. Plus, there are fewer parts than the conventional style oil pump. Now, the way that the oil pump can affect oil flow is through the relief valve. This valve relieves excess pressure produced by the oil pump. This excess oil pressure is bled off and goes back into the oil pan. The point where the relief valve is activated varies between engines, but usually it's around 55 to 70 psi. It's necessary to limit the total amount of pressure because damage could occur to the oil filter or to seals if the pressure is excessive. Now, I'd like to note, too, that oil pumps are designed to produce more pressure than is typically needed by the engine. The reason for this is to assure that the oil pump has sufficient capacity during extreme situations. Now let's take a look at the oil filter and the bypass valve. The oil filter should allow all the oil in the system to flow through it, but there are some situations that could occur, especially when the engine is cold, where it is necessary to bypass the filter to assure an adequate oil supply is available to the engine. When the pressure rises past a certain preset point, the bypass valve opens and allows oil flow to go directly to the bearings without filtering.
How about if the filter is dirty and plugged? Will the bypass valve work then?
Oh yeah, definitely. In fact, I was just going to mention that. Failure to change the filter at the recommended intervals can result in a totally plugged filter, allowing dirty oil to be circulated through the engine. Let's take a look at the results of bypass valve operation one more time. Here's normal flow with oil going through the filter. Now here's the flow when the filter is plugged. Notice how the filter is completely bypassed.
Does the bypass valve vary in its opening and closing, or is it simply open or closed?
It'll vary in its degree of opening depending on the amount of filter clogging. It won't typically be just opened or closed. Remember, the bypass valve doesn't just work because the filter is plugged with contaminants. Because there are times, like when the oil is cold and thick, when it's necessary to bypass the filter to assure adequate flow to the engine.
I can understand why this valve would be very useful in the winter because the oil is thicker when it's cold than when it's warm.
That's right. Another point to note is the positioning of the bypass valve in motorcraft filters. It's right at the top, where the filter contacts the mount. The reason for this is that when the bypass valve activates, the contaminants contained in the filter cannot get back into the engine. Some filters have the bypass valve mounted in the bottom of the filter. When the bypass valve activates in these filters, some contaminants are washed out of the filter and go directly to the bearings, and that's not good. Well, we've gone over the system and major components that are found in all lubrication systems. There's a few more components that I want you to be familiar with.
Oh, what are they?
oil coolers, windage trays, and piston cooling jets. Let's take a look at some oil coolers first. Not all engines use oil coolers. They are sometimes found on high-performance engines, and those engines that are used in high-load or high-stress conditions, such as police cars, off-road construction equipment, stationary engines, or in some cases, truck engines. They can also be of different designs. This one uses engine coolant to absorb excess heat. Others are designed like radiators and depend on airflow to dissipate heat. Another point that's important for you to be aware of is the positioning of the oil cooler on the engine. Why do you think it's placed after the oil filter rather than before? Well, the reason is that oil filters best when it's hot and thin. When the oil is cool, it thickens, which would make it more difficult for the oil to pass through the filter. Also, it's very important that the temperature of the oil is low enough to adequately cool and lubricate the bearings. This next component is a windage tray, or baffle as it's sometimes called. It fits into the crankcase and prevents the oil from sloshing around, especially during hard cornering. If the oil sloshes around and contacts the rotating crankshaft, it can cause oil foaming, which can be damaging to an engine.
Why is that damaging?
Well, when oil is foaming, it means that there's air in it. If the air gets into the oil lines, it means that a continuous flow of oil is not getting to all the components, which would cause damage. A good early warning signal for this condition is upper engine noise caused by collapsed lifters.
I see what you mean.
This last component that I wanted to show you is a piston cooling jet. These are often used in diesel engines to cool the piston head. This jet sprays oil against the bottom of the piston while the engine is running. By doing this, it absorbs excess heat and takes it back to the oil pan as it drips off.
That's interesting, J.C. I can see why that would be necessary because of the high compression ratios that diesel engines have.
That's right. You're picking up on this lubrication system information, and that's good.
Well, thanks. You've been a great help.
So, John, you want to discuss diagnostics, checking oil pressure, and motor oils in general?
Yeah, J.C., I want to learn more about diagnostics, what the oil service ratings mean, and the SAE viscosity grades. That's probably stuff I need to know and don't.
No problem, John. That's what I'm here for. Let's start with diagnostics and failure analysis, because they go hand in hand. To begin, there are two complaints that you'll hear about related to the engine lubrication system, and they are the engine is using too much oil, or the indicator light or gauge is acting up, usually by indicating low oil pressure.
Well, what causes these things to happen? What are the causes of excessive oil consumption and low oil pressure?
Well, let's look at them one at a time. We'll start with excessive oil consumption. There are essentially three reasons for oil loss from an engine. One, it can burn in the combustion chamber. Two, it can leak from the engine. And three, it can pass out of the crankcase in the form of a mist. These reasons for oil consumption essentially have three causes, which are engine speed, engine wear, and poor sealing caused by bad, failed, or improperly installed seals or gaskets. Let's look at high speed first. Now, high speed produces high temperature, which causes the oil to thin out. The thinner oil is more able to work past the piston rings into the combustion chamber where it is burned. Also, the high speed exerts a centrifugal effect on oil feeding through the connecting rod journals. Because of this, more oil is fed to the bearings and is thrown on the cylinder walls. Now, there's just a lot more oil there to control. And this isn't helped by the fact that at high speeds, a condition called ring flutter can occur. In this situation, the rings begin to shake rapidly because the piston is moving so fast. Now, when this flutter occurs, the oil control ring can't function effectively and lets more oil get by into the combustion chamber. That final reason that I mentioned, oil misting, occurs because of increased crankcase ventilation and increased blow-by. High engine speeds mean that there's more blow-by. Plus, because the engine components are moving so fast, there's usually a lot more oil mist floating around the inside of the crankcase.
JC, I know I'm changing the subject a little bit, but before we go on and discuss any more, could you explain the crankcase ventilation system?
Oh, sure, John, I'd be happy to. Let's take a look at normal operation first, such as idle, cruise, or light acceleration. Under these conditions, fresh air comes in from the air cleaner. Air flows through a closure hose, through the valve cover, and into the engine crankcase. The fresh air and blow-by gases flow out of the engine to the PCV valve, which controls the flow of air and blow-by gases into the intake manifold. Heavy acceleration and high speed are different because there's no introduction of fresh air into the system. What you've got is a high volume of blow-by gas causing pressure to build in the crankcase. Part of the blow-by gases flow through the PCV valve to the intake. The other part of the gases flow through the closure hose to the air cleaner and into the engine.
That's very interesting, JC, and I can see how some of the oil could be drawn into the airstream at high speed, especially if the engine is worn and there's a lot of blow-by.
Good. Some of the points you should remember about PCV valves is that they aren't used on all engines, but most engines do have them. It's very important that the PCV valve is checked as part of the scheduled maintenance. And if the air cleaner is equipped with a filter for the PCV system, it should be serviced at the recommended interval. Now let's take a look at why oil consumption occurs with increased engine wear. Worn bearings, especially rod bearings, are a good place to start. Now, as the bearing wears out, the clearance between the bearing and the journal increases. In the case of the rod bearings, this allows more oil to be thrown onto the cylinder walls. This means there's more oil that has to be scraped off by the oil control rings. But it's also aggravated by cylinder wear.
It is? How?
Well, you know how a cylinder gets tapered in a high mileage engine? The top inch of the cylinder is a larger diameter than the bottom.
Yeah, I've seen that.
What happens is that the oil control rings have a hard time conforming to the taper. Look here. The oil control rings can't expand and contract fast enough to scrape all the oil, especially at high speed. Coupled with bearing wear that allows more oil onto the wall, you're going to see increased oil consumption.
How about ring pressure against the cylinder wall? Does that have an effect?
It sure does. As the cylinder and rings wear, the force of the rings pushing against the cylinder wall is reduced because of the increase in the cylinder's diameter and the slight decrease in ring size that are the result of wear. The reduction in the ring pressure against the cylinder wall allows more oil to get into the combustion chamber. The increased burning of oil in the combustion chamber also adds to the problem because it allows carbon to build up, foul spark plugs, and generally accelerates an already poor situation.
I can see where that would definitely increase oil consumption. How about valve guide wear?
Sure, that'll cause increased oil consumption because as the guide wears, the clearance increases, allowing more oil to go into the combustion chamber.
I guess bad valve seals wouldn't help either, eh?
No, they wouldn't. And that brings up the third cause for oil consumption, which is poor sealing. Let's start with valve seals. Bad valve seals allow more oil to get into the guide. And if the guide itself is worn, it only compounds the problem. The typical problem with valve seals is that they can harden and crack with age and can just plain wear out, especially if the oil and filter are not changed on a regular basis. Another cause of oil leaking past valve seals is improper installation. If a special tool is called for installation, make sure you use it.
Okay.
Now, bad valve seals cause oil leaks on the inside of the engine. The same is true of other seals and gaskets. If they allow oil to leak out, it can result in a complaint of oil consumption. Let's take a look at an engine. There are several places where oil leaks are possible, the major ones being where seals and gaskets are present. Some areas to look at are the rocker cover gasket, intake manifold gasket, camshaft expansion plug, the oil filter gasket, the oil pan gasket, fuel pump gasket if the pump is mechanically driven by the engine, the front crankshaft oil seal, the rear crankshaft oil seal, and the front cover gasket.
What's the best way to find an oil leak?
Oil leaks can sometimes be difficult to find, especially if they're in a tight spot. But the best way to do it is to wash the engine clean, especially in the area where you suspect the leak is originating. Then you can run the engine and look for the leak. Of course, the thing you want to remember is that leaking oil always flows down.
So if you notice oil dripping all the way down the back of an engine, you can figure your leak is up in the valve cover or intake manifold area. See, you could replace the rear oil seal thinking that the oil leak is at the back of the engine, but the leak is actually above the rear seal in the valve cover area.
What you're saying is always check for oil leaks from the top of the engine down.
That's right, John.
Are there any tools I could use to help in finding oil leaks?
Sure. Let's go back to the bench. This is the Rotunda high-intensity black light oil leak detector. What you do is add a bottle of this fluorescent additive to the oil, then run the engine. After the engine has run for a while, you shine the black light into different areas to see where the oil is leaking out. The fluorescent dye will show up under the black light, and you'll see exactly where the leak is coming from.
It shows you exactly where the leak is coming from before you tear anything apart, right?
It sure does. There's some other things you should be aware of, too, when it comes to fixing oil leaks, and that's using the correct gasket materials. Obviously, you should always use Ford gaskets and seals for your repairs. And when you're installing a gasket or seal, make sure that the sealing surface is clean and in good condition with no gouges or imperfections that could affect gasket or seal performance. This is especially true on the crankshaft front and rear seals. Damage to the sealing surface will result in rapid seal wear and another oil leak condition. Also, you should be aware of the silicone, rubber, and liquid gasket materials. These are very handy for oil pans, rocker covers, front covers, and many other components that require gaskets or seals. These materials are often called for in the shop manual. Don't ignore these instructions.
Okay.
Make sure you use the recommended gasket material. There's also Perfect Seal, which is real handy for bonding gaskets to components.
Yeah, I've used Perfect Seal a lot, especially on oil pan and rocker cover gaskets. It really holds the gasket in place and makes assembly a lot easier.
Okay. We've covered the first major complaint that is most often heard, which is the engine is using too much oil. Let's take a look now at the second major complaint, which is the indicator light or gauge is acting up, usually by indicating low oil pressure. There are typically two causes for the oil indicator to show a problem. Either there's low oil pressure or the oil pressure sensor or gauge has failed, causing excessively low or high pressure to be indicated. Take a look at this example of an oil pressure warning lamp and gauge. If the light flickers erratically or comes on part of the time, or the gauge doesn't show a consistent low pressure, either there's not enough oil in the crankcase or else the oil pickup is not consistently picking up oil. If the light stays on all the time or the gauge is consistently low, it indicates very low oil level or extremely low oil pressure. If the warning light comes on or the gauge reads low, the first thing you should do is check the oil level, which should be in the cross-hatched area. If it's extremely low, add oil. But if it's normal, you should check the oil pressure with a mechanical pressure gauge. Let's hook one up. You should always check the oil pressure with a mechanical gauge when there's any question about oil pressure. The mechanical gauge is only going to register if there's oil pressure. They can't get a short circuit like the electrical type of warning light or gauge. Also, note that the oil pressure gauge is usually attached where the oil pressure sending unit is mounted.
How should you check the oil pressure? Engine cold, engine warm, high RPM, low RPM?
Engine oil pressure is usually checked at 2,000 RPM with the engine at operating temperature. You can find out the exact conditions by checking the shop manual engine specifications. See? It's right here. The oil pressure should be 40 to 60 psi at 2,000 RPM with the engine hot in this application.
I never knew that spec was in there.
Well, you do now. Go ahead and start it up, John, and we'll check the pressure on this engine. It should still be warm from running in class. As you can see, it's well within specifications.
Yeah.
Go ahead and shut it off, John.
Okay. What are the main reasons for low oil pressure, JC?
There's quite a few, John. Let's go over to the disc player and I'll show you there. In the first place, you should be able to hear a low oil pressure problem.
How's that?
Well, look here at this lubrication system. Look at the flow. It goes from the oil pump to the filter to the bearings, then to the lifters, and finally up to the upper end of the engine. In a low oil pressure situation, that oil pump probably will feed the bearings with enough oil to prevent damage for a while. But because the lifters and upper engine components are further down the line, they'll be affected first by low oil pressure.
So what you're saying is that I'll be able to hear the lifters and rocker arms clattering as one of the first signs of low oil pressure.
That's right. You're getting it. Now, these are the things that can cause low oil pressure: insufficient or excessively thin oil, high fuel dilution, a weak relief valve spring in the oil pump, a worn oil pump, excessive bearing clearance, a broken or cracked oil line, such as the one going from the pickup screen to the oil pump, obstruction in the oil line going from the pickup screen to the oil pump, or a defective oil pressure sending unit or gauge. Of course, you'd know if it was the sending unit or gauge after checking the oil pressure.
I'm curious what you mean by obstructions. What can obstruct the oil flow?
Well, it's anything that prevents the flow of oil through the engine. The most common is plain old sludge. Here, let's look at this oil pan. This is a real extreme example, John. Now, how's this for sludge contamination? When the drain plug was taken out of the pan, nothing came out. It was all sludge inside.
What caused this?
The owner of the vehicle probably didn't follow the oil quality recommendations or maintenance schedule. That's most likely what allowed the sludge to build up to this extent. Here's another example. Look at this pickup. It's totally clogged by sludge and metal particles.
Where did the metal come from?
From the pistons, rods, bearings, and other components. This engine was starved for oil, but the owner kept driving it until it came apart.
Wow, this is really bad.
Here, look at this cam. This lobe is wiped out. And compare these lifters. This one's all dished out. Probably no oil was getting to it.
No oil caused this.
Sure, or it could be poor oil or not following the maintenance schedule. It pays to follow the oil quality recommendations and maintenance schedule in the owner guide. Which brings up the next thing we should talk about: preventive maintenance on the lubrication system.
One more question, though, about oil pressure.
Sure, what's that, John?
What causes excessively high oil pressure?
Well, excessively high oil pressure can be caused by a stuck relief valve, an excessively strong relief valve spring, a clogged oil line, a cold operating engine, excessively heavy oil, or it could be caused by a defective sending unit or gauge. But just like on low oil pressure, you'd figure that out when you check the pressure with a gauge.
Yes, I think I would. You mentioned excessively heavy oil. What do you mean by that?
Yes, I did. And I also mentioned excessively light oil for a cause of low oil pressure. You've got to use the proper recommended oil in all Ford engines. That's part of preventive maintenance, which is what I want to talk about next. Preventive maintenance of the lubrication system primarily means following the maintenance schedule in the owner's guide and making sure that the correct oil is used. Now, Ford is very explicit about maintenance schedules in the maintenance schedule and record log. There are two maintenance schedules, Schedule A and Schedule B. You may remember unique driving conditions, or Schedule A, as severe service. Let's take a quick look at what constitutes Schedule A conditions. Short trips of less than 10 miles when outside temperatures remain below freezing. Towing a trailer, using a camper or rooftop carrier, or carrying a maximum load. Operating in severe dust conditions. Operating during hot weather in stop-and-go, rush hour type traffic. Extensive idling, such as police, taxi, or door-to-door delivery service. And high-speed operation with a fully loaded vehicle. If any of these conditions are typically encountered by a vehicle, then it affects the maintenance schedule. Because under these conditions, the engine oil and oil filter should be changed at the driving interval specified in Maintenance Schedule A. This is typically 3 months or 3,000 miles, whichever comes first, instead of the normal 6-month or 7,500-mile interval. You know, the worst part about these Schedule A driving conditions is that most of the people who drive like that don't even consider it severe. It's in the owner guide and maintenance schedule.
but they just don't consider their driving habits severe or hard on their vehicle. That's where it's important for a guy like you to know what's severe so that you can remind owners whenever possible to maintain their vehicle at the specified intervals.
You're right. I can see where that would be important. I'm curious, though. What kind of damage can be caused to an engine if it's consistently run a quart low on oil? I see that a lot.
Yes, I know. It's a prevalent problem today. The bottom line is that you've got less oil and therefore less additives to do the same work, and it will cause problems. Let me show you this graph so you can see what I mean. This graph shows that in testing over a 64-hour period, oil thickens dramatically if it's 1 quart low, as opposed to a full crankcase. Note that at 64 hours, the oil in the full crankcase has hardly been affected, whereas the viscosity of the oil that was 1 quart low zoomed right off the chart. This thickening is caused by oxidation of the oil and results in heavier deposits and increased instances of ring sticking. Even the finest oils available today fall victim to this problem when the oil fill falls below the recommended level. Remember, all the oil change intervals assume the customer uses the recommended quantity and quality oil.
When you say viscosity, you mean the thickness of the oil, right?
That's right, John. In the example we saw, the oil gets over 10 times thicker than new oil. That's like going from a 5W30 to over twice the thickness of a 60 weight oil.
JC, could you explain the SAE viscosity grades and the other information on the oil containers?
Sure. In fact, we'll do that next. Always refer to the owner guide for proper engine oil recommendations. Now, in this owner guide, it states that you should use a Motorcraft oil or equivalent oil that meets Ford specifications and API service category SG. The use of SG in combination with other letters, such as CC or CD, is also acceptable. Now, you don't have to worry about the CC or CD rating if you see them, because they apply to diesel engines. It's the SG you should be concerned with. It will appear inside the API service symbol on the container of oil. If it doesn't say SG, don't use it. This API symbol also contains the SAE viscosity grade in the center and any claims for energy conserving that apply along the bottom. Up until 1988, the highest service rating was SF. SG was not specified until the 1989 model year. Before 1980, SE was the highest rating. The point is that you must always add oil that has the minimum API specification recommended in the vehicle owner guide. This means that you can put SG-rated oil in an engine that only calls for SE, but you should never put SE or SF-rated oil in an engine that calls for SG. SG-rated motor oils offer substantial benefits over SE and SF products in both current and older model vehicles.
Why do the oil ratings keep changing?
Well, there's a lot of reasons, like increased maintenance intervals, advances in lubrication technology, and other things. But the main reason is the increased stresses put on the lubrication system by emission controls. Face it, engines are running hotter. They're smaller. Contaminants can't be vented to the atmosphere. The lubrication system is just faced with a very tough job to do. Also stated in the owner guide is that for vehicles 1989 and beyond, never use non-detergent oils, never use oils labeled API SA, SB, SC, SD, or SE. Also, oils labeled only SF are not recommended. And finally, never use additional engine oil additives. The next point I want to make concerns the SAE viscosity grade. This indicates the thickness of oil at particular temperatures. According to this owner guide, for most ambient temperature operation, SAE 5W30 is the preferred oil. In instances where hot weather, above 100 degrees Fahrenheit ambient is encountered, it is advisable to run an oil of a higher viscosity, such as SAE 10W30.
Okay.
Remember, the SAE rating is in the center of the API symbol. You should also look for the Roman numeral 2, following the term energy conserving. This means that the oil is formulated to help improve fuel economy, which is a very desirable characteristic.
Now, one of the things that I certainly recommend against is second-guessing the lubrication engineers and not using the recommended oil viscosity. There are plenty of straight-weight oils, racing oils, and all kinds of things that typical automobiles don't need. Just put the recommended oil in the crankcase, and it'll do just fine.
What does the W stand for on the 5W30 and 10W30?
Actually, it originally stood for winter, but what we use it for today is to indicate an oil's cold start capabilities. The lower the W number, the easier the engine will start in cold ambient temperatures. For instance, a 5W30 oil will allow an engine to start much easier when the temperatures are below 0 degrees Fahrenheit than a 10W30 oil would. It's very important for the oil to flow, especially at cold ambient temperatures.
Well, JC, you've answered a lot of my questions.
No problem, John. I was happy to do it. Do you have a good handle on lubrication systems now?
I sure do, and thanks a lot, JC.
My pleasure.
Hey, I guess you really did receive quite an education.
Yeah, I really did. That was great.
Hey, by the way, who was the instructor?
It was J.C. Barnes or Burns. No, it was J.C. Barney. That's who it was.